So I would like to start. So unfortunately, the downloading of the data on a USB drive still takes some time. Iga, next to you, there's a hard drive. No, the large one. Yeah. There's at least the part for the second part of this hands-on session already on there. And I just let me have a quick look. So yeah. So I'm going to share this around. So there's this ESDC subset2.zar dataset on here that that we're going to use in the second part of the hands-on session. And I think for the first part, you just need to watch me doing it because yeah, I can't. The USB drives are too slow at the moment. Yes, of course. Hopefully. Like this? Is it okay? So yeah, I'm going to give an introduction to JuliaEO and the processing of large data, and I'm also going to talk a bit about setting Sentinel-1 TIFF files up so that they can be used in JuliaEO. And so first we instantiate our environment. They should be available on the apparently in the pull request for the JuliaEO GitHub, and so first we look into chunk data. So the data has to live somewhere on the disk, and so as Fabian mentioned yesterday, in geospatial data, we often have the problem that data that is close in space is not close on disk. And therefore, depending on your use cases and on the analysis you're doing on the dimensions, you can have certain data to, you can have problems because there's some access penalty, and we're going to look into this if you load a netcdf file. So we're using the netcdf package here, and then we're using disk arrays to look into the chunking sizes of the data. And so we now have a compressed netcdf file with a size of 1440 by 720 by, so this is the spatial size, and then we have 1794 time steps, and the chunking is as maps. So it's one map, and then it's the next time step, and it's the next, and so on. So therefore, it's very fast to just access the single time step and the whole spatial pattern, but it's very painful to access the whole, just access one time axis. Because the problem is that the computer needs to access every single chunk of your data set. So this is roughly 5 GB of data that is then just accessed all at the same time, and it has to decompress the whole thing, and then it has to load just takes the one time step and then has to decompress the next chunk and takes one number. And just as a comparison, I have the same data chunked in smaller spatial subsets. So it's I think it's a chunking of 90 by 90 by 184. And there we see that the chunking of the maps is a bit slower, or it's quite a lot slower because it's some orders of magnitude slower, but the access of single time steps is a magnitude faster, two orders of magnitude faster. So here with disk arrays, we can have a look into the different chunkings. And so with this each chunk, you get basically the indexes into every chunk. And so we see here that the chunking is like the whole map in lot and longitude and latitude, and then a single time step. And then disk arrays knows this internal chunking structure and therefore can implement special MapReduce functions that can then be used, for example, for the mean. And you can see that even though so this is going to take half a minute, but even though the access of single time series is very slow, the MapReduce over the whole time axis has a similar speed, because it's like it's accessing every chunk once and then making sure that you're doing the MapReduce over all pixels at the same time. And then so this works quite easy for the mean, but it's not as easy for the median, because to compute the median, you have to have the whole time series in memory, because it's not a MapReduce, I think, anymore. So we can see here that we can take views into subparts of the of our spatial grid, and then this is very slow, because it has to do a lot of these deep compression and access patterns that are not fast. So it would be better to just do to always read a certain size of memory, and then just do all the computations on that memory, and then read the next chunk. So we can here just define the latitude ranges that we want to do, so that we have a certain amount of memory loaded at the same time, and then you can do this MapReduce over these latitude ranges at the same time, and then compute that for these multiple steps, which makes it already a lot faster. And so this is basically what what I should have done. This is basically what JuliaEO is doing in the background. So it's making sure that your computations are done efficiently for these very large data sets. So here we have this the netcdf file loaded as a JuliaEO data set, and then we can access this layer, the one layer of, so that we can just load the data, and we see that this is a JuliaEO with the longitude, latitude dimensions, and 1,748 time steps, and then so this total size is basically the maximal possible amount of data that would be there. So it's just the product of the sizes of every dimension times the size of the element type. And so we can see here that this this is doing a map slices of the median. So it's just apply the median on every slice of data. And for the slicing, we're using the time dimension. So here you can specify these dimensions as strings, or as named strings, or as axes in the in your JuliaEO. And we see that this computation is taking roughly a minute, and this is basically what we with the naive approach of just, where was it, doing this with the view. It's taking the same time for the whole data set as it would have taken for a 4x4 or for 4 grid cells. So it's a lot faster. And then it's also doing taking care of the parallelization. So it's using the distributed package. So that's the standard library of Julia, and it's using so here we just add some processes to do the to have some workers to parallelize the data access and the computations. Then we have to make sure that every package that we're going to use is available on every worker. And then we can do just the same operation, and now JuliaEO is going to use all of the available workers because they're available in the background. And I don't know why, but this is failing for me in this Jupyter notebook at the moment. I didn't find the error yet. But it's definitely worked in my normal setup. It works quite smooth, and then you can even use different. You can use Slurm or other cluster managers to access or to set up the workers, and then it's going to take care of the workers. And then so because of this, because the data set access is so painful, it might make sense to rechunk the data if you're going to use the same patterns over and over again. So if you know that you're going to use this data set as a time series or for time series analysis, it might make sense to pay this chunking cost once and save the whole data set in a new setup, in a new chunking, so that you can then have more streamlined access for the whole experiments that you're doing later on. And to do that, you can use the set chunks function, which takes your data set and then it takes a named tuple of chunk sizes for every dimension in your data set. And then this is still lazy, and then you could you can then save this as a SAR file somewhere on disk. And now for that, I mean, this is now a compromise chunking of, okay, we don't have every time step, but we also don't have just the whole time series for very small spatial regions. So it's just, it's an in-between compromise, but I'm also using a lot of the whole time series and then just a smaller or smallish spatial region in my daily work. Should be that, right? So this is so this should show a progress bar in a, hopefully. So yeah, you see here it's are there any questions so far to the chunking while we're waiting for the computation to end? Now you see that this was a bit faster than so this took now on the chunk data took 51 seconds, while just doing the whole thing here took 1 minute and 16 seconds. So it's a reduction of 5 seconds. So it's a bit of a reduction for this data set. I mean, yeah. So it's always yeah, interesting to think about what are your best, what's the best compromise you would get to do all the analysis you're planning on. Yeah. Okay. So for the second part, unfortunately, I forgot to wait. Maybe I can. Let me check whether I can just copy these data sets into your USB drive, so you might be able to follow along. It's done already. Okay, good. So the next part is about combining multiple TIFF files into a YAX array, so that you can then can continue working on them. So my use case was having sent a lot of Sentinel-1 data that was already preprocessed, and then combining that into a spatial cube. So you have a data cube of longitude, latitude, time, and polarization. There's a folder with S1 data. And I just realized that I should get my charger cable, otherwise it's going to be ending soon. So to work with the Sentinel-1 data, we have this folder S1 data. And then we just specify a polarization. So we first want to do this on the VH data. And then basically these lines are just to walk through the folder and find all data that is find all files that have this polarization string inside them. So I assume that the data is all following certain naming pattern, and then I'm just filtering for the data that has this VH here. So this is so we have a few metadata in the file name already. So it's the sensor type, it's the acquisition mode, it's the orbit, it's the time of acquisition, it's the orbit number, it's the polarization, and then it's some pre-processing steps. And then I'm going to first pass the data from the time information from these file names. So you can do the get date, and then you search for these patterns of the year information, the month, the date, and then the time stamp. And if we do that, we get a vector of datetime objects that say, okay, this is 3rd October 2016 and 16th of January 2020, and then some timestamp. And here you see that these timestamps are really really near together. So it's basically it's the same acquisition, and and then it's another acquisition 2 years later, or actually 4 years later. And so as a precautionary step, I'm going to sort the dates by time, so and also the files, so that we really know that we have a sorted time series, because before the data has been sorted by just the path, and this might be failing. And then we're grouping the data into different times. So we say, okay, we have a time difference of 200 seconds. So we assume that everything that is just 200 seconds apart is just going to be actually the same acquisition. It's just going to be split by ESA because for the data handling. And now we are going to use the GDAL VRT system to just combine multiple, to combine them spatially. So to do the mosaicing, and to do that, we first define this temporary path where we have a path for every subgroup of the data, and then we save the data into VRTs. Okay, wait, I did not. I did load that, no? Now this should work. Now you see that we have these interactive data sets of ArchGDAL. There's the information of the input data, and so we see here the data set width and height in pixel, and some metadata information. And now we build now we save these, now we build these VRTs for every subgroup. So it's this, so now we're spatially mosaicing the data together. Now we have a set of, so we have a vector of 2 ArchGDAL data sets. So we have one for every time step. So there's and in every data set there's this, okay, we have one file here, and we have these two files together that are basically just near each other, and then we have the other time step with the same setup. And now we can use this GDAL build VRT with the separate keyword, just to say, okay, keep everything separate in separate bands. So otherwise, VRT would, or GDAL would try to mosaic them together spatially, or just averaging them. And here we say, okay, just group them next to each other and keep them apart. And now we have this raster data set of ArchGDAL, and now we can use YAX-array to just the YAX-array type to convert it into YAX-array. And now we only have this band information, but we already knew the dates that we used for that. So we have these, so we just take the first time step of every subgroup, and then we construct the time axis here with these dates, and then we can just use this axis in our cube, so that we then have a the whole that we have now a data cube of the 5 of the latitude longitude by time axis. And this works as well if you would have a lot more data or a lot more time steps that you would like to put together. And now we can see that we have this cube chunks. So we can check, okay, what's the chunk size of the data set, and now we see it's basically similar to the problem we had earlier. It's a very small, even here it's a small spatial chunk, and then it's just one time step. So because And that's because they basically all came from single TIFF files. And now we can use this the set chunks function again to say, okay, we want to have more. We want to have a chunking in space, and then we want to have just have the whole time series, and that's what we're doing here. And then you see, okay, the new. This is the new chunking, and then now you can use SafeCube to say, okay, and now I'm going to save this into a ZAR file, and then we can use that to do our further analysis and work with it later on. Or you could as easily replace this by your .NET CDF, and then it would then it would also just use the NetCDF backend to write the data too. Okay, are there any questions about that? Or is it all clear? Okay. So then I'm going to give a general introduction to Yax and the MapCube function. So I hope that at least some of you now have the EastDC subset 2 ZAR file on your computer. No, it's there. Okay. That's a bit of a shame, but I mean, we can try to use the maybe we could try to just use the Earth Data Lab. Yeah. Yes.
How do you normally decide the number of chunks you want? It's diverse depending on like what you're processing, and is it heavy to like re-chunk the data when you figure out you divide it by wrongly?
That, I mean, yes, because it's basically, I mean, you need to touch the whole data set again for the rechunking. So depending on that, I mean, with the data set I'm normally working with, it's okay because it's small enough. But for larger data sets, it's just getting more painful. And so I would say it depends on the use cases on the analysis you want to do later on. So the aim of the chunking is to put data together on the disk that you're normally using together. So if you're mostly doing spatial analysis or spatial averages or something like that, it makes sense to have them together. So to have a larger spatial size, chunking size. I'm using mostly time series, and I'm mostly using the whole time series at the same time. So for me, it makes sense to just have a chunking that is rather small chunks in space, but then the whole time series. And I'm also not too sure about good heuristics to find the perfect chunking size. We're planning on looking a bit into that. So seeing how, I mean, I think it might also depend a bit on your general computing setup. But so you don't want to have too small chunks, because then you would have to open too many files all the time. But you also don't want to have your chunks too large, because then it's just not feasible, because then you have to load them all the time, and then they are just too large for your memory. And then depending on the analysis you're doing, whether you have how much sub steps you have, because normally you're not only loading one data set, or you're loading your data set once, and then you're doing computations, and you have temporary results that are of similar size some of the time. So that's also something. So you don't want to be too large, because then you will blow up your memory. So yeah.
But it's quite easy to rechunk. Okay, it will take time, but this function that the representation is
Yes.
one line. So it's one line.
It's easy, but it might take some time depending on the size of your data. That's just.
Yeah.
And I mean, there's also use cases. I mean, for example, for this Earth System Data Lab that we are.
But it's not like you're rechunking data set between oh, I computed this format, and then I need to do some other.
No. What we did for this for the Earth Data Lab, which is a huge, so it's a spatial chunk. So it's a global data set of a lot of different variables, so climate and other things, and because you have this cost, they are available in both chunkings.
Ah, okay.
So that's another way you can deal with that, basically, but by just paying disk size. Yeah. So just basically blow up your whole, just double your disk size of the whole data, because you're just going to do this again. And there are even I'm not sure what the status of this is at the moment, but there was an extension for the ZAR specification of having multiple chunkings in one file, which would help, because you can then have the same compression. So the data could be compressed together, because it's the same data, it's just different chunkings. Yeah. Okay.
This leads to a slightly different question. Just out of curiosity, is it possible to have like irregular chunking?
Yes.
Okay.
Maybe Raf can say a bit more about that. Yeah. No?
Okay. Exciting.
I'm not sure why updating the registry is taking so long at the moment, but if you don't have the data and want to follow along at least a bit, you can use the EOS Data Lab package and load the ESDC. So it would then be just but I'm going to continue a bit, and then no, I wouldn't. Yeah. Oh, okay. what? Okay, yeah, that's not working at the moment. Okay, it's not. So yeah, that's so we're now looking into this. So we're just using this this data set. So it's a subset of this system Datacube that you could get from the EOS Data Lab package. We're just doing C equals ESDC, and this would be hosted on the on our cluster in Jena. And but here we have this data set with 720 by, so it's again the latitude longitude grid and the same time steps. And here we have different variables. So we have air temperature, land surface temperature, GPP, and yeah, so it's just 5 of them. So we want to do construct a cube out of them because they have all the same grid. So this is the main difference between the data set and the YAX array, is that in a data set you can have multiple subcubes. So you have multiple subcubes and they might have different dimensions. So you could have one cube with latitude, longitude, time, and then another cube that is just the static information of land cover, for example. And with the cube function, you just convert the whole data set, or you try to convert every variable that has the same dimensions and put them together in a data cube, and then you have this new variable dimension which has as access these cube names basically. And here you see that the size would be 33 gigabyte if you would load the whole thing into memory, but actually this could include missing values. That's not that in the end, but it's and it's also not as large on the computer. So on the computer, this is now just 5 gigabyte, but but it could blow up to that. And so this is just a lazy representation. And now we want to do some computations on that. So we have this map cube function, and so the map cube function takes this inner function. It takes the input cubes, it takes the input dimensions and the output dimensions, and so the inner function always has the structure of x out, so the output, then the input, and then you can have other variables or other keyword arguments. And here we're just applying a median, so we're filtering the nuns, and then we're just going. Then we see just compute the median if there is some time information there, which was not none, all none. And it's important that you always, so it works that by just updating this output variable, so it's doing the computations in place. This makes it faster because you can reuse the memory you allocated for different chunks. You can reuse them all over again and again. And why is this taking so long? Okay, I think this is taking now some time because I don't have any threads or any parallelization going on. So it's interesting. Okay. Oh. Okay. Here we run into the problem of apparently having missing data with that. The problem is that apparently in this data set we have missing values and none. So we have to filter for both. Otherwise, it's not going to work at all. Okay, that was not it, I think. Damn it. I'm going to try it one last time and then I'm going to move on. Because I don't see the yeah. Okay, so I think it's now working, but I'm going to move on and explain the next step while waiting on this computation. What actually? Next, okay. So with this map cube function, you can also combine multiple cubes or have an output of multiple cubes. So the idea is that so here we have multiple outputs. So we have a time series output, we have a mean output, we have a a standard deviation. And we have one input. So we in this example, we're computing the normalized time series by subtracting the mean and dividing by the standard deviation, and while also saving mean and standard deviation of the whole time series. And so here you see, so in the inner function, you have these multiple outputs, and then you have to make sure that you're assigning values to these outputs. And then you're computing, so you're updating these, and then you can update the mean by the mean function and so on. And to define this in the map cube, in the outer map cube, you define one input dimension. You say, okay, I want to input time, and then you have multiple output dimensions for your different outputs. So you have the time for your whole time series, and then you can specify a path where the output data is saved, because this is all going to be loaded chunk by chunk. So it's doing the computation and it's saving the computation per chunk somewhere. And so if you don't specify this is going to be in some temporary folder, which is going to be deleted later on. But if you specify this, you can specify the exact location where the SAR file that was computed is going to be saved. And you can then also specify the backend, and you say, okay, I want to overwrite whatever was there already. And you can even mix different backends in the same mapcube call. And so you have this, so have the means and the standard deviations, and save them in netcdf. And then you just have a tuple of output dimensions. And here you say, and then you get back a tuple of cubes, and these are then computed. And here you see that the outputs are a cube of the same size as the input. You have and then you have two cubes of where the time dimension is just reduced. So it's you lose the time axis because you have reduced over it, and it's just going to do this computation for all your variables, because you didn't specify the variable axis. And I'm not going to run this now because somehow my setup is really shaky. I don't know why. And so far this was all just some statistics, but you can basically run every Julia function that is available on a Yax array. So you can specify some user-defined function, and then it's just going to apply this over all the input that you specified. So we want to do some, so we could do some time series decomposition. So here we have the what was it? It's the GPP over time, and then you can separate this into a trend component, a seasonal component, and whatever's left. And when we now want to compute this, we have the input dimension. So we specify, okay, use it on the time, and then we can specify the output dimensions. And here we are basically we're computing from one time series, we're computing 3 time series. So we are increasing the size of the dimension. And so therefore our time, our outdims is the time. And then we can specify a categorical access. So it's just a new access to save these different time series, and we can give it a name, and we have the scale. We just call it scale, and then we have the we have a vector of dimension names. So it's just seasonal, trend, and remainder. And here again, we can specify the path and the backend, and then we specify these the inner function. Again, it's just x out and x in. So we say, okay, if any of these is none, we're just returning missing, and then we compute this time series decomposition, and then we save them in the different slices of the output. And I'm there to run it again. Do you have any questions so far about the mapcube function or the accelerator functionality? Yes. Wait for the mic.
Yeah. So the functions you've shown here mainly like collapse, or like you go along one dimension, but how is it like applying a window in one of the dimensions? So
might be coming to, no, we didn't. Okay, yeah, I can show you that. It's actually quite easy. So you want to implement speckle filters, no?
Yeah, so actually there's I one time saw an article about a spatial temporal speckle filter, where you look at a window in space and then also a window in time.
So what something. You can do is
maybe that would be like the advanced case.
So you can do speckle.
Yeah, so something like a local mean in both space and time.
So it's just a mean, right? It's actually it's just like so you could do something like that. I mean, you could do a lot more if, yeah. I mean, in regards of kernel, but then you would have a And then you can, so you have this moving window type, which can be used for the setting of the dimension.
Yeah.
And then you can specify, you can even specify the so
Yeah, the size.
the size in both sides. So you could say, I think 5 days before and 0 afterwards.
Okay.
So you can have shifted moving windows, or you can have unequal moving windows, and then you can do I think. And then if you just specify, if you only have so if you only specify one, it's going to be quadratic.
Yeah.
It's basically the idea of like, okay, just let me interrupt this computation we tried earlier, but and then see that whether this is actually working. Wait, what? It's not. Okay, maybe I was misremembering that this works, but it should. And now we should do map cube of S1. You loaded the Sentinel-1 data earlier, right? So we can do yeah, dangerous live coding, but okay. Yes, I didn't rename the data earlier, so this should be X. This should be Y. Okay, and now it's up to
The missing values.
filtering. I mean, now you will have to basically do the fit bit more special things in your inner function. But that's just the idea of this moving window of these moving window things.
Can you try and go up to the filter mean filter? Just
wait.
Yeah. Yeah. So here the xn the size of xn would like correspond to the size of the moving windows, like, and also the dimension.
Is it not showing? Yes, so the size of the size should be 5 by 5 by 9 by 9.
Okay.
Oh, 6 by 6, right? Oh, wait. Yeah, I'm not.
Yeah.
So yes, and then you can also, so it's normally just loaded as a plain array type, but you could do it. So you could specify the R type. So I think it should be here, like this. You can say, okay, I want to have an Yax array in the inner function.
Okay.
Because then you can have a, and then you could use the same functionality. I mean, I think it would not be that fast to then also use mapcube in your inner function, but at least you would know the dimensions.
Okay.
And so on. So you would have a named dimension. Yeah. I'm not too sure how good this would work then, but at least it's possible, and it's like sometimes it's nice. I think it's going to do a new size, so it's not. I'm not sure whether it's going to inherit the x and y coordinates from the the position. Rather like 5 till 0 to 5 or something like that. But it still has the dimension name.
All right. Thank you.
Then another thing that we can that we provide in Yax arrays is this cube table interface. So it's just converting your data into a table, and then you can do certain computations on that. So something is not right. Okay. So here now we have a we have the data set we had before, and we also have a data set with all the country information. So it's just it's a rasterization of the countries of the world, and now we can construct a table out of that by just saying, okay, cube table, and then this is going to be the name, and then you say, okay, I want to have this variable represented as GPP in my table, and I want to have air temperature to meter represented as TR in my table, and I want to have the countries the other country file represented as country, and so you can combine multiple cubes into one table, and so you get an iterator over subtables. So this is going to be a bit nested because it's all taking the chunking into account. So it's being these, I think the 78 subtables represent or are aligned to the chunking of the data set, and you can then access one of these subtables, and you see that you have this schema. So you have a GPP, TR, country, and then you have the longitude, latitude, and time information. And this is all lazy, and you're going to only load the data as if you would access it. So now we have a subtable, and then now you see that you have a you access all of this of this temperature information, and you can then convert it to a data frame or something else, because it's all implementing the tables interface. So every subset is a tables interface, or every subtable is a tables interface. And now you see that you have this huge data frame of or this data frame of GPP, TR, and then the country. And now you can also do computations on these tables using the weighted online stats or the online stats package to do some aggregation computations. Now we again, okay. I shouldn't have tried to use multiple processes. This does not want to play with me today. Yes. Okay. So let's not do that. Let's just do this. So yeah, while we're loading on that, I can explain the next step. So the idea is to have this. So you have this cube fit table function that takes a cube table that we constructed earlier. Then it takes a weighted online stats aggregation method or type. And then you can say, okay, I want to fit the air temperature. And then you can specify, okay, I want to fit it by country. And I weight by the cos D of the latitude. And I don't dare to do that now, because I assume it would take quite some time if it took a minute with multiple processes. So so by this you get the mean by country for every, so the mean air temperature for every country weighted by the size of the degree pixel. So that's basically the idea. And then you can, and now you can then convert this to a data frame to look into this and see that. And you can also do it by time. So you can have this. You can basically say, okay, I want to split it by months, and then you can say, so you would get not only one value per country, but you would get a value per country per month of the year. So it's now the average monthly average air temperature, all with a weight. And you can then also and you can use at least some of the online stats functionality with that, and all it's all quite fast because it's online stats, so it's only using so it doesn't have to load the whole time series before doing the statistics, but it's doing that as on the go, I would say. So, of course.
I was just wondering whether the weights, I see here that you provide them as a function of latitude. Can you provide them in the form of like a data set itself, like either a column in a table or an array that you would index into?
I think, yes. I mean,
maybe it's not specific to your package, really, but the weighted average.
Basically just that's a good question. Yeah, you might have to jump to some hoops there to okay. Just but I think what you could definitely do is you could load your data into your subtable.
Right, that's I was thinking, yeah, essentially adding columns to
you can basically, I mean, you here in this cube table, you're specifying, you can, so this whole example was starting here, right? So here we have just the data set. So it's a global data set with with multiple variables. Then you have a rasterization of the countries, and then which is rasterized on the same grid. And then you have and then now here you can specify this cube table, and then you can say, okay, I want a GPP, and I want to, and then here you rename the things again, and then the countries, and then you could have here your own weights.
Yeah, I think makes sense. I think it'll do it for me. Thank you.
That should work. Yeah. Are there any other questions? No? Thanks, Simon. Yeah.
It's more just now. So like, what is the big features that you're working on now, and like where do you see it, like it going? What are the challenges?
So I think so the next step is basically getting rid of our own or moving our own cube type to the dimensional data thing. I think one of the things on the agenda, because it would be nice to have this overlap of, I mean, Rasters is doing a really good job in providing all of the indexing features, and also getting stuff on the GPU. And I mean, there's just different focus areas that we had, and we are more focused on really larger data and trying to use that. So it would be nice to just combine these efforts and try to get our, so I think it's clear that our data cube, our Yaxo type is just not as good as the dimensional data things. So that's a step. And then Fabian is currently started to work on a rewrite of the whole backend of. So I think the idea is to have everything as moving windows. So the idea is that to just have one streamlined interface, or like one implementation in the background that's just doing the moving windows, and then if you want to have the whole time series, you just set your moving window size to the whole time series, and then do the computation then. I think these are things that we're currently working on. In the long term, I would like to explore more in combining good information more into the computations, and see whether we can basically see that you only do the computations if your grids are aligning, or you also do the resampling only if it's necessary, and go more into an abstract computation thing on some of that. But that's really further into the future. Yes.
Yeah, I was going to ask a question you might have answered earlier, and if I was distracted, I'm sorry for that. But was wondering your performance if you had sort of benchmarked your package against, I think the Python solution would be something like Dask and XRA together.
Mm-hmm.
Do you want to comment on performance or benchmarking of that?
I haven't personally did a benchmark yet, or not these. I mean, that's also something that we should be doing, to actually know some of that. From what I heard is that some things are not possible on XOA and Dask, at least have not been possible, because especially in the combination of like spatial and temporal together, or doing, I think one of the examples was doing a PCA for every pixel and then over the whole time series. The problem is, I think, I'm not really sure about this, but I think some problems arise because Dask is trying to compute the whole computation graph for every pixel. And then if your data is large enough, it's just going to fail. But yeah, I need to have more, actually to properly comment on performance differences, I would have to actually do the computation or the comparisons. So we have not done that.
Okay, thank you. Yeah, I would like to highlight that this is very important in that way, what you're doing, because that's one of the workflows that the Python community really wants from us. And so I think this is, this is really important work.
Are there any online questions? Okay, if there are not any more questions, then I think we can just close it, right? Or is there? Okay. Then we close the hands-on session for now. Okay, thanks.